Good afternoon, and welcome to the HP Science Lecture Series. Before I introduce our guest speaker, I would just like to take a moment to clarify what we mean by 3D printing. It's not wholly unreasonable, when you take the context of 3D printing and HP, to think of ink or toner being deposited on the outside of a 3D object. That's not what we mean. 3D printing, in the context of what we're talking about, is the creation of real physical objects. So I just need to clarify that, because it has been noted that 3D printing, just taken on its own, and along with HP, doesn't necessarily result in the right interpretation. So the format's going to be approximately 40 minutes long, and then we'll open the floor to questions. But if you have a question, could you please raise your hand, and we'll pass a microphone to you so that everybody can hear. So I'd now like to give a warm welcome to Siavash Mahdavi, who's going to give us a very interesting talk on 3D printing and lattice structures.
Okay, well, thank you very much for the kind introduction. Okay, so my name is Siavash Mahdavi. I'm from London, just traveled in today. And I work at a couple of companies, one called Within Technologies and one called Digital Forming. And we work within the industry of what is known as 3D printing. Now, before I go into the details of 3D printing, I want you to kind of understand why it could be important. Here is an X-ray of a femur bone. In this X-ray, you can see that bones are not solid. They're actually porous. Now, the primary reason for this is that as human beings, we consume energy just like vehicles, and being porous means you're more lightweight and you can move more easily and you need less energy to fuel your body. What the body does need to do, though, is ensure that in some regions where it needs to be stronger, it has more dense bone, whereas in some other regions where it can be less solid and more flexible, it can have more porous bone. So looking at this X-ray here, you can see in this area, known as the femur head, the bone here is much more dense, which counteracts any loads coming in from the hip bone down the femur stem. In other areas, such as here, you can see there's not much going on. So you can see nature is very efficient in how it designs us, both kind of in the cells and biology, but also in the bones. How can we take and be inspired by nature in designs of everyday objects? Well, going into the basics of 3D printing, this is a paper printer. You input two-dimensional data, and out the other end comes a two-dimensional image. And you can have laser printers, you can have desk jets, and various other types. 3D printers look a little bit more like this. And here, instead of having 2D images, you have 3D CAD designs that get sent to a machine that then manufactures them in 3D. Now, the video I'm going to show you is of a specific type of additive manufacturing or 3D printing machine called the EOS M270. This is a metal machine. It actually prints, let's say, in metal. Here you can see you start with a 3D CAD design of the object you want, and you send it to this machine. This machine then actually takes the 3D design, slices it into layers that can be as small as 20 microns in size. It then takes each layer of your design and sends it to a laser that melts powdered metal and contours and fills in that layer of powdered metal as per your design. Now, continuing this process layer by layer, now it may take only a couple of hours, or it may even take a couple of days, but layer by layer, you can actually get a fully three-dimensional object to grow. This can be in various materials, and materials are increasing every single day. We have a range of metals. We have aluminiums and titaniums and stainless steels and more fancy things like Inconels and Hastelloy X, to a range of polymers and even ceramics. So what happens is, as this part builds up, it fuses to the layer below, and once the part's finished, all you need to then do is in fact simply pull away the excess powder from the part and revealing the solid part finally on the build platform. This is then a fully melted metal or plastic component that can be used in aerospace and consumer products, and we're going to be showing a wide range of applications for this manufacturing technique during this presentation. So here it is. This is a tool insert for a cup, actually, with conformal cooling channels on the inside. So going back to the reasons behind why we would even think about 3D printing. Here is an animation we've created of the same kind of 3D printing process, but this time of a much more complex design. This is what we call a lattice structure. It's a structure that cannot be made using any other manufacturing technique. It has double angles, it has very long aspect ratios, and it's something that cannot be made using casting, milling, injection molding, or anything else. You can see this actually almost resembles a material in that in some areas, let's say at the end, it has much more porosity, whereas the other end smoothly gradiates towards a much denser design. Now that was just a cube. We can move on to more complex designs here. And what we do is we can take any component and we can change its material and mechanical properties by filling the solid volume of objects with these lattices. So instead of having a solid block, you can instead fill it with a very complicated lattice, just like bones are filled with the bone cells that are porous or more dense. You can have the same thing with any day-to-day component. What this means is I use less material, it's more environmentally friendly, it's cheaper to build, and you can have a variation in mechanical properties. You can have, as you can see here, a much denser and much stiffer component, or you can have it much more porous. You can even have density concentrations. So right in the center there, you can have a component that is much more stiff and rigid, but smoothly gradiates to becoming much more flexible. This can allow you to have variable cushioning, for example, in footwear, which is something we'll show you in a moment. You can also have a variation in different types of interconnectivity of these lattice structures, which themselves enable different types of properties, be that cushioning, flexibility, or stiffness. Just finishing off this animation here, you can see that we can change the lattice topology, thicken it up, and in the end, we in fact emboss our logo into the lattice using these density concentrations. Now, standard software and what we call FEA, which is finite element analysis. I'm not going to get too technical, but standard software has been matured for decades to standard manufacturing techniques, such as casting, milling, CNC, injection molding, and it's very good at doing that, but it's not amenable to this new manufacturing technique of 3D printing. And this is for two primary reasons. Firstly, it doesn't allow you the design freedoms that you now have with 3D printing, but also it doesn't understand some of the restrictions that do exist. And so what you end up with are parts which may be as simple as what you see on the screen here, but are actually very difficult to build. What we have done at Within is develop software that's specific for additive manufacturing. And just showing this very simple video demo, we can take a solid component, such as a very simple, what is known as a cantilever beam, which is an object, essentially just a rod fixed at one end to a wall with a load pulled at the other end. And what you want to do is make this as light as possible. Now, this kind of structure is present in this building, it's in the ceilings, it's in boats, it's in cars, it's everywhere. What we want to do is make this as light as possible to make it cheaper, use less material, be generally more efficient. So what we do with our software, we can fill it with this complex lattice structure, which we can now build because of additive manufacturing. But what we want to do is ensure that when we build this, the part works. So we need to do what is known as finite element analysis, or essentially simulate the part to ensure that it works. So what we do with the software here is we've actually simulated the loading conditions, or how the part is stressed and loaded under normal day-to-day use. And we ensure that we then create this very organic, as you can see, slowly optimizing internal structure here, which is now replacing the solid. These colors are representing variations in stresses. So in some places, the part is actually highly stressed. There's a lot of pressure there. So it needs to be thickened up slightly. In other areas, there's not much going on. Just like in the bone, some areas aren't really doing much. So there you can pull material out and ensure the part's as light as possible. As you can slowly see evolving here, the graph on the top left, you can see is going down. That's the weight of the component. So what we're doing here is this solid object is slowly becoming lighter and lighter and lighter, but we're ensuring that at any one point, this solid object meets the requirements. Now, we've also ensured other things such as file compatibility with the machines and understanding the mechanical properties of such components. Now, the great thing about additive manufacturing or 3D printing is that complexity has no cost. If you were to manufacture this and CNC it, the more holes you make, the more expensive it is, because it's a subtractive process. In fact, the solid block is the cheapest thing. Anything you then do to it is adding to the cost. With 3D printing, it's the exact opposite. You start with nothing. So every little bit of, every powder of material you add to it is costing you more. So in fact, what you want to do is add as little as possible, and all this complexity, all these internal structures actually aren't really costing you much in computation or in time. So here you can see we made a component that has a slightly fluid and varying density structure that meets our requirements. Now, just going through what these lattices look like, I'm just going to give you a few examples. Here's one we call the grid topology. It looks like a very simple grid. On the bottom right corner, you'll notice what we call the volume reduction coefficient. It's a very fancy word, but essentially, its value of 0.14 means that this component is only 14% of the weight of the original. That's a big, big weight decrease. Here's another one. It's called the X topology. This one's actually very good for metals because metal 3D printing has its own rules where you actually need to ensure that you'd never go below, let's say, 20 or 30 degrees to the horizontal, and so you have to ensure that the part's still buildable. Some other structures here. I'll just move through these slowly. But I have some samples in front of me now as well. This one is made in a flexible polymer. It's a polymer 12, and you can see it has cushioning in one direction while lateral stability in the others, and you can feel free to have a look at this after the presentation. Another use for these lattice structures, which you'll see in the case studies, is for what is known as osseointegration. This is the combination and infusion of bone cells into such structures. This is used for orthopedic implants. So when you have an orthopedic implant and you actually implant it into the bone, it's important, and I'll explain this further during the presentation, that the bone cells actually grip on and latch onto the surface as tightly as possible. And what we can do here is create structures such as this that actually mimic the trabecular structure of bone and actually have the right pore size and distribution so that bone cells actually fuse into these 3D printed products. This is the example I showed you earlier. You can see here it's an interconnected wave of lattice structures, and these pins here actually go into the holes above as the part depresses to ensure you still have lateral stability as the part is taking this cushioning. Now, this is the first case study we call a liquid lattice. This is a very big, chunky metal component, and essentially all it's doing is you have two holes at the top. They get connected, and they come out the side, right? So you're mixing two fluids, and you bring them out the side. But you have all of this material. It's a big waste of material. Now, what you want to do is ensure that you can 3D print this object, but make it as lightweight as possible, make it as efficient as possible. So what we do is we can run this through our software, and we say we want to be able to withstand any internal pressure within the pipe, because the pipe is transporting fluids, and we want to ensure that any load along the top surface is also withstood. So here, as I've shown you before, we can simulate the part. You can see the stresses within this internal lattice, and then the software starts designing something that can then be sent to the 3D printer. Now it starts with a small, tight lattice around the tubes to ensure that the tubes themselves are supported, but then starts supporting the top and bottom as well. And you end up with an object that looks like this. Now this was designed fully automatically with the software. It uses a combination of artificial intelligence, evolutionary computation, so it's actually inspired by nature. It's not designed like this because it happens to look nice or it happens to look natural. Using evolutionary algorithms, you actually do end up with more natural designs. Here's a photo of the part, and I have it here with me as well, so you can have a look at it afterwards. It was manufactured in stainless steel, it's fully solid, and this is now only 22% of the weight of the original. So it's a big, big weight reduction. Now, in aerospace, they have something called the buy-to-fly ratio. This is typically 10 to 20%. And what this means is that they buy this much material, and by the time they chop it off and then they mill this bit and they add something else and whatever else they do, only 10 to 20% of this actually flies. 80 to 90% of it actually gets chucked away. So this is a lot of wasted material. With this, the buy-to-fly ratio is kind of 95%. There's barely any material wasted because as you print, it prints, as you saw in the video, all the powder that's not melted, you just shake back into the machine and you reuse. So it's only very little amounts that you may have to machine off. Otherwise, this part is almost 100% used. So it's, again, great for the environment. Now, we showed this at an exhibition last year, and a lot of people, actually some Formula One teams, thought this was a heat exchanger. So we decided to play around with heat exchangers, and we designed one that looks like this. Now, this one looks very different. A heat exchanger essentially is a radiator. It can be put into a car or vehicle, and it's used to either cool or heat fluids. What you can see here is we have teardrop-shaped inlets along the top. Fluid comes in, snakes around this heat exchanger, and comes out the other side. This part is built in aluminium in one piece on the EOS M270. Now, looking at the insides, inside the tubes, we've created an obstacle course of turbulators. Now, this is actually used to turbulate the internal fluids, because as the fluid runs through a channel, what ends up happening is the hot fluid will continue to run through the center while the cool fluid is nice and cool around the outside, and you have what you call laminate flow, which isn't good because you're not actually being very efficient. So having an obstacle course means that as the fluid runs in, it's constantly being tumbled, and you have more efficient heat exchange. So we were able to manufacture heat exchangers with these obstacle courses within the tubes, 3D printed in one piece, in one build. Now, we also have the air running vertically here, and you'll note by the angles here that the air has to be forced through. It's not easy, and this is actually a conceptual heat exchanger for a Formula One car, and there you actually want to force the air through the component. Now, with this part, this was essentially, again, 95 to almost 100% material usage. So no manual work, no manual labor. You just slice it off, and the part's done. This actually makes it amenable to being manufactured in countries where labor costs are much higher, because there's actually not much labor. Now, because this was designed digitally, you can assemble it digitally to fit any shaped volume. So in a Formula One car, you don't always have a nice big square block of volume to put your heat exchanger in. You have an awkward corner in the back, and you want to fill it in there. What you can do is you can replicate this to fill that corner to whatever space you have virtually, manufacture it or 3D print it in one piece, and just put it in there to fit. Now, moving on to medical, we've designed finger implants. These are in titanium. And what you'll see here is the bearing knuckle surface here and this stem. Now, this stem actually gets inserted into your finger bone. And again, you'll see what we call here the lattice volume. And this is for osseointegration. So just to remind you, if you have a bone and you insert a solid metal rod or a metal implant into it, what tends to happen is the bone cells move away because they essentially sense that the implant itself can withstand the stresses, and so they don't need to be there. Nature knows that, okay, this bit seems pretty strong. I'll move away. I'll make myself porous. But essentially, they just start loosening the implant up, and the implant has to be replaced. And this is why hip implants and a lot of other implants, they actually won't give you until you're of an older age because your bones are constantly moving. And so if you're only in your 30s or 40s, they won't even give you those surgeries because they'll know it'll loosen up within 6 months. if we have structures such as this that are actually porous, what the bone does, instead of moving away from the implant, is fuse right into it. So it just grabs it. It goes fully into the object, and you get full osseointegration into the implant. So these are finger implants here, some other visualizations, and we've done some other types of implants as well. Moving on to cranial. Now here, cranial implants are very interesting because if you have a metal implant in your head, it's not very flexible, and your skull tends to be flexible, so it doesn't feel very good. And it also can feel quite cold as well. What we can do is we can print in a material called PEEK. It's actually an aerospace material, but it's a plastic, essentially. And you can put it in there, and it can have some sort of flexibility, so it feels much nicer. We can also put this lattice structure throughout the part so that over time, your bone actually starts growing through this, and you end up with complete bone recovery through your skull implant. So these are just some visualizations here of analysis on the part just to ensure that if this is implanted, that it would work, and we showed that it did. And this is the implant itself, so here's some visualizations of this lattice structure that conform to the shape of your cranium. Now, this is very interesting because if you were to even try and manufacture this in other ways, it's very difficult because everyone's head's a different shape. And there's a very good chance that a crack in your skull is going to be a very different shape to someone else's too. And so customized implants here are very important. So what we can do is by taking CT or MRI imaging of the crack, we can take this into software, create this structure, send it to a 3D printer, print the exact shape you need, and place it in. These are some mechanical testings of the part. We also infused it with a special gel that encourages bone growth. And these graphs here actually show, through testing, that we did get successful bone infusion into this implant. And here is a visualization of what it would then look like if implanted into the skull. Acetabular cups essentially is a fancy word for hip implants. It's the most popular type of orthopedic implant. And here, just running through some visualizations of simulating what these look like, essentially is this part here, made in titanium. It's a cup, so it's a half a tennis ball, essentially, and it gets implanted into your hip bone. And we can create these very nice, interesting surfaces that have bumps that are rough, that can be impacted into the hip bone, but also have the holes and channels to allow osseointegration. Now, we've moved on from this kind of design to this one here. Now, looking at this surface, it looks, I'm just zooming in here, it looks almost like a chemical process. It looks like someone's taken a metallic surface and somehow chemically etched away to create this organic structure. But this is actually a 3D design. Every little strut, every little hole there has been designed in 3D. It actually exists in a computer. It was sent to a machine, and if you build 100 of those, they'll all look exactly like this. We're actually able now to get to a resolution where we're mimicking metallic foams of a size of, let's say, 200 to 300 microns in pore size. So this is great for bones, and we're doing a lot of testing now to see how well bones now infuse into such products. This next object here is a tibial tray. This is a knee implant, which I have in front of me as well. It actually looks like Saruman's tower from Lord of the Rings with the trees around it. But essentially, that gets impacted into your bone this way, and then your knee goes on top. And those little tree-type structures there are just, again, for more grip and more bone ingrowth into those regions. Now, this one's a very interesting project, paper pulp tooling. Now, these are the only words you'll see in my presentation. I think it's because they're quite profound. Every year, 480 billion cups are thrown away in Europe and America. I didn't know this, but paper cups are not recyclable. It's because they have an inner coating of plastic, and this actually means that it costs so much to try and tear that off again, they just go into the tip. What we've been able to do with 3D printing is create a mold that can take paper pulp, like you get in egg cartons, and compact it to such a density and create a fiber matrix where it's waterproof and watertight without the need for this internal plastic liner. This is the prototype of the cup itself. We can even do paper cup lids, which is very interesting because plastic lids tend to be carcinogenic. And because of the manufacturing technique, we're actually able to make this cheaper than current paper cups. So now, through artificial intelligence, complex 3D designs, lasers, powdered titanium, and 3D printing, we're able to make a paper cup, but it's cheaper and it's biodegradable. So this is one of our very interesting projects. Now moving on to something completely different, high-heel shoes. We were given, and I feel very guilty about this, government funding last year to develop the world's most comfortable high-heel shoes. So this is a video. You start with a 3D foot scan to take the contours of the foot, because everyone has different kind of shaped feet. You then put on these 5-inch heels, as you can see here, and then you walk on a treadmill, and we can, at several times a second, scan the pressure distribution that are exerted on the inside of the shoe. And what we then want to do is create variable cushioning, like you saw the variable density of the bone, to counteract exactly those loads. So here's just some analysis here. Essentially, the red areas are places of high stress, and the blue areas and black, there's not much going on. So what you want to do here is essentially in those red areas, put more cushioning so that you have a more comfortable shoe. Some more imagery here of the average and the center of gravity and the exact force values. Now, this is the midsole of a standard high-heel shoe. You can see it's made of about 5 or 6 different materials. This requires labor, it requires assembly, and it means it's not so recyclable because you have to have someone tear these all apart. Our aim is to replace that with this. It's made in one material, it's just one plastic, but it has a variation in density. So you get the stiffness where you need, but you also get flexibility and cushioning in other areas. The sample I have with me isn't of a high heel shoe, but this is of a running shoe. So this here you can see, I don't know if you can see from there, but this is variable density. So in some areas it's very stiff, but it smoothly gradiates to becoming much more flexible. So you can pick the cushioning where you need, but the flexibility where you don't need, and the whole part's manufactured in one piece. So more images here, and this is the shoe assembled. This is just one of the first prototypes. We have actually advanced a little further than this now. Now moving on away from aerospace and automotive and medical, moving on to consumer products, because this is a whole other aspect of 3D printing. And I'm going to introduce digital forming, which is my other company. And here, 3D printing kind of opens up something completely different. So in the first half of the talk, we were talking about complex designs, variable density, performance. Now we're moving on to something else, which is customized products. Now, with standard manufacturing techniques, such as injection molding, you're spending 10 to 15 to 20,000 pounds just on one tool because you want to make one part, and when you keep opening and closing this tool and spitting out the same part, ideally millions of times. With 3D printing, you can make every single one different. That doesn't cost you anything. So why not make them all different? For consumer products where you can express yourselves, as you can see with the trends here, in either sunglasses, at Oakley, or crystals, or even running shoes, why not customize? Now, with all of these products, they're only talking about color change. You can pick a different leather color, or you can pick a different crystal color, but you're not changing the shape or the form of your 3D product. Now, I want to just describe what mass customization is. On the left, we have mass production, where essentially someone builds one thing, and people either like it or they don't. So they may like it a bit more in certain aspects, but on others. Then we have what is called as variant production. So they'll give you 10 different styles, 10 different colors. And you can kind of cluster towards the one you like the most, but essentially it's not perfect for you. Mass customization, the idea there is that You literally are involved in the process, and you get exactly what you want. At Digital Forming, we've created a manufacturing infrastructure where brands, consumer brands that you all know very well, can interface with distributed 3D printers around the world. There are thousands of 3D printers out there. People don't have access to it. Brands aren't going to invest in millions of pounds of 3D printers just like that. They're going to want to have some evidence. They want to get into it slowly. So what we actually get to do is we make people have access to the distributed manufacturing technique and collaborate with their users. So here I'm going to show you some interfaces. So here, for example, we can do customized glasses. Have you ever gone into a shop, or have you ever opened up a magazine and said, wow, those glasses look really cool. As soon as you go, you put them on, you just look stupid. You look like a bee, or they look too small, and you only wish they were just a little bit smaller. What you can do with this is, why not change the shape? Why not kind of slightly tuck them in and bring them down and make them fit exactly to you? Get the lenses exactly cut and sent to you. There's no reason why you can't do that with 3D printing. There's actually no added cost. If you were to 3D print it of a certain size, why not slightly change the size? Make it exactly fit you. You can still have the brand's name if you want to follow a certain brand style, but you can actually still add your own individual flair to it. This animation here, on the left, you can see a little black line. And this is a tool where someone can, by slightly changing the curvature of the line, design different vases. So imagine you want to design a vase, or have a vase at home, or a cup, or whatever else. Why go to a shop and browse for hours and pick the one that most closely fits your style, when you can just sit there and literally just sketch a little line and just design your own, and you have the way of kind of adding your personal values to the product and then design it yourself. So here you can see just how one simple line revolved in 3D can give you so many different designs. And every single one of these is viable. You just send it to a machine and you get it printed. Imagine going to a shop to buy a nice light for your living room. You can buy the aluminium kind of stand, but then you want to customize the actual light fitting. On the left, again, you can see a 2D interface where you can very simply stretch and skew and twist these primitives that are then replicated to create this light fitting. And you can make it exactly how you want. You can almost kind of do a little doodle and sketch on the surface, and this can then emboss vases or cups or anything you have at home. So you can really add your own values to components. And what happens is, when you've finished, and this is the key, once you've designed this either through a website at home or at a terminal within a store, and you press print, it finds the printer that's about to go, and it sends it to that machine. So just like airplanes, if an airplane flies and there are empty seats, the airline is losing money. If a printer is about to go and there's some empty space in the printer, that's wasted space. What we can do is we know where all the printers are and what they're doing. So as you're about to print something, it says, OK, there's one down the road. It's about to go in 2 minutes. I'll send to that one. It negotiates a good rate. You get the best price, and it sends it to that machine. And this isn't just locally, but it's also globally. So if you send a gift to your friend in New York, well, it's not going to be built here and then packaged and flown all the way there. It gets digitally sent to the closest machine to them in New York. It gets built there. They can go and pick it up. Now, with customization comes some dangers, because you have to ensure that the part still functions. Here is an example of a lemon squeezer. The white areas on the right are areas that can't be changed. So the squeezing mechanism, if someone shape changed that and skewed it out of proportion, it's not going to squeeze a lemon. So with consumers that are non-experts in the things they're necessarily going to buy, you want to ensure that they have a nice experience where they can manipulate some areas, but they can't shape change others. So the brown areas there are parts that can change, but the white areas aren't. Now we have some terms here. We call the original design object ODOs, and we call the co-design objects CODOs. So what we have is the original designer and the co-designer kind of almost interacting with each other. So you can see this one design at the top has resulted in these little babies of different lemon squeezes along the bottom. And these are them 3D printed, and even colored one in purple as well. Here's some iPhone covers. You can see kind of different twisty shapes, and you can really have a play with them. And now this video is of a desk light. And you can see the interaction scenario. So this is a fully 3D experience. It's actually online. So you can go onto a website and manipulate this through your browser. You can see it's a full 3D experience. And what you have here is what we're trying to do is make a very, very simple interface. So you get as much design freedom as you can without making it too complicated. And what we're doing here is we're allowing people to replicate little kind of what we call dynamic skins on the surface of this light and change their shape and change their style and then change the color and really have a lot of fun and be able to express themselves with this light that they're going to buy, I don't know, their mum or dad, or have it for themselves. So here you can see you can kind of twist the angles, you can change colors, you can view it from different angles, you can see close up whether you like it or not. You have a lot of detail. It's actually very continuous. And at any one point, the software is intelligent enough to know whether this part meets all the 3D printing requirements, because if it gets far too delicate, it may break, or if it gets too long, it may topple over. So it ensures that though you have the biggest amount of experience you can, it doesn't actually limit or doesn't infringe upon the viability of the product. And when you finish this part, you can see on the right there's a photo now of the light itself, and on the left, the 3D CAD. Here, different visualizations. So it's the same Odo, but 5 different Kodos. And here's some photos again. So you can see how one object actually is so wide in its variety of shape, color. I mean, you probably wouldn't even call these the same light. But what this means is that designers that interface this kind of audience now are not just designing one shape and saying, this is my design and take it or leave it. They design the shape and the interaction scenario around it. They have to say, okay, this is mine, but then also you can stretch it slightly like here, you can twist it, you can add this shape, you can put a butterfly here, and you can make it bright pink. And all of these things are what a designer now has to be able to handle. And what we can do is you can collaborate essentially with these designers. So let's say your favorite designer, let's say Philip Stark, you want to design with him the next lemon squeezer. And as you slightly making it longer, in the bottom first it says designed by Philip Stark. As you stretch it, it says 90% designed by Philip Stark, 10% designed by you. And as you stretch it a bit more, and it can keep changing until essentially it can get to a point where Philip Stark decides, you know what, if you go beyond this, I don't want to be associated with this design, so it can all be yours, it's just yours, and you can put your name on it. But it allows this kind of interaction with the design. Here's some other phone covers we designed. So you can see here different types of skin, different types of techniques, different colors you can play with. We've also are kind of creating our own, it's more like a beta testing site for us to test our different interaction scenarios. It's called ucoder.com, where you can actually go online and you can interact with these products and have a play. Just wrapping up, moving towards the future of 3D printing, because all of this that I've shown you is today. It may look like the future, but this is what's happening now. Only a few weeks ago, in August, we worked with a team associated with NASA to do the first 3D printing of a component at zero gravity. So there's a machine called the Bits for Bytes. It's a machine that essentially extrudes through a thin nozzle like toothpaste, and it grows like this. And they're able to extrude these parts out of the 3D printer as long as you like. So this changes the paradigms of kind of space centers, where you have to come in with the whole construction essentially assembled into a spaceship and assemble it and take it out of the airplane, or sorry, the space shuttle. Here you can just have the powder or the material and extrude whatever you want out the end and actually create your own structures. So here this video is as a design we made where we can essentially extrude an infrastructure that has fuel coming out one end so that spaceships can dock and fuel up, but at the other end has electricity, and it actually has a variation in density or flexibility, so it actually almost can take an impact. And this is quite a conceptual design, but you can see how this is integrated in one piece and how you can potentially manufacture in these multiple materials. Now, they did build a part, only about this much of it in the machine, but it built it at zero gravity, and this is a video now of a NASA astronaut actually standing on the part after it was printed, and here he's at 2G, meaning he's twice the weight he would normally be, and you can see the part is able to withstand his weight. And as the gravity slowly shifts and then goes to 1G and slowly to 0, the part becomes weightless and it starts to float. So that's quite nice. So it's very, very lightweight design. So this is micro laser sintering. You can see it can get very small. This is a metal. This is stainless steel. You can use this to make very intricate watch components. This could actually be used, for example, to prevent people copywriting things and actually taking people's designs, because it's very difficult to then get access to such intricate designs without access to this kind of 3D printing. You can see it here. And finally, we're moving beyond the kind of titanium implants that I mentioned and more towards kind of biological. And there have been moves towards printing, biological organs and hearts and lungs, and I think, maybe 20, 30 years down the road, but I don't see why we can't actually print full organs for ourselves as well. And that's it for my presentation. Hope you liked it. Thank you. To welcome any questions.
Hi, is it possible to have any hollow spaces without the powder in inside? Because you said you shook it off afterwards. I couldn't see how there could be any sealed hollows.
Okay. There are quite a few different 3D printing techniques, and only a few use powders. So the ones I tend to work with do tend to use powders. So there, if you have a hollow cavity, once you take it out of the machine, it will be filled with powder. So you have to create an escape hole and take the powder out. There are other techniques such as SLA, where it's a UV curable resin, and there you're essentially taking a part out of liquid. And so as long as the liquid can drip out, it's fine. The part I showed that was flying at zero gravity, that doesn't use powder or resin, it's actually extruded through a thin nozzle. So there the part doesn't have anything that has to be removed.
What is the largest object that you can make with current techniques? What is the largest size?
Probably as big as this table. So it's about as big as a person in one piece. And that would be the resin-based systems. There are some metal systems that are getting close to that, using kind of arc-type welding, where essentially it's extruding the metal and welding as it goes, and there it's as big as the gantry or robotic arm that you can manufacture. But 3D printing at the moment is more amenable to smaller components of high value.
My field's non-destructive testing, and I'm used to looking at large metal components, and if they're made by forging or casting or welding, I know what sort of defects there's going to be, so I know how to design my inspection techniques to see if A, they contain manufacturing defects, or B, when you use them, if they generate in-service defects. Mm-hmm. I'm actually slightly boggled trying to think of how the heck I'd inspect something like this. Have you ever had any thoughts or experience of that?
Yeah, this is a common problem. So what we were doing, if you remember the structure I mentioned for osseointegration, where you have holes and cracks of 200 or 300 microns in size, there, if you do an inspection of that, it'll just look, if you do an X-ray, it'll look like the part's completely cracked and shattered. It's very difficult to inspect. So that's why when we move on to aerospace and automotive, we are actually slightly increasing the size of such structures to things a little bit more kind of this kind of size, which are more easily inspected. There are other techniques that we're kind of innovative, new techniques that we're looking to employ in collaboration with some of our clients, but there isn't anything that is currently established that is best suited to such non-destructive testing.
I wanted to ask about the costs. As you said, conventional technologies like injection molding can bang out millions of parts, so the amortization across the parts is very small. I'd guess that if it's taking hours to make parts, machines are going to have a much more limited amount of parts they could produce, and I'd guess therefore that there is going to be some higher costs. So I just wondered, how do you see the costs of these parts compare to really high volume techniques like conventional sintering and injection molding and so on?
Well, it's going to be very difficult to replace injection molded parts because we're talking about pennies compared to pounds. And it's not really suited to that either, because with injection molding, you can just spit these out the end of the machine very quickly. With 3D printing, you have to create a whole batch, get it ready, and then have to be pulled out the powder. There's a lot of stuff that has to happen. So that's why you have these two different, I believe, avenues for 3D printing. There's a very high value, very complex industrial applications that just cannot be made in other ways, where lightweighting or bone integration or other things are very important. Or you have the other way, which is the customization approach, where you're adding so much value to the component by individualizing it that it well exceeds the added value or the added cost of the manufacturing.
How hard is it to actually make your building blocks, like your powder or your resin or your UV gloop? I mean, how hard is it to actually get these parts to build all these things?
To manufacture the raw component, or to manufacture the part?
The powder. I mean, how hard is it to make your powder or resin or whatever you use?
The powders are made in standard metal powder manufacturing techniques. It's nothing new. So people that are already currently making powdered metals, you can just use the same suppliers. You wouldn't do it yourself. The polymers, the powdered polymers are a little different. You have to have a blend to get it just right, and there are suppliers out there that do it for you. So as a user, as a designer, or as a consumer, you wouldn't need to get involved in that.
I can understand how you can melt on a new layer of metal, but how do you do that with ceramic or paper? When you're making a paper cup, you're adding layers.
No, the paper cup wasn't itself 3D printed. The tool that created the paper cup was 3D printed in titanium. So the paper cup, normal paper cups are actually, you have to make the paper first, then you cut it, then you roll it, then you laminate it and do everything else. What we're doing is we can make paper cups in the same way that you make egg cup holders, essentially by having a slurry of paper pulp and sucking it through a complex system that actually compresses the paper to create the form. So to go away and move from what egg cup cartons look like and get it compressed and get it to have the kind of aesthetics and properties of a paper cup requires this complex tool, which was made during 3D printing. So the paper wasn't actually made in that way. There are actually paper printers. I think one of the companies is called MCore, and what they do essentially is they transfer, and you can just feed it with photocopy paper, A4 paper, into this machine. It takes that one layer, it slices out the shape you want, cuts it and removes the paper, and it puts some super glue, another paper on top, and it keeps slicing, and it goes like that, and it actually looks really nice. It's very high resolution, and they now use this for creating lasts for shoes. Because when you want to create a leather shoe, you have to first have the wooden last to wrap the leather around, which is actually very expensive to do. And now they can just manufacture this layer by layer, using this layer, essentially laminating paper stacks on top of each other.
Hi, is it possible to make movable objects like a spanner?
Movable objects?
Yes.
With hinges?
Yes.
Yeah, you can. Well, this one moves here, the plastic one. I don't have any other ones on me here, but you can. In plastics, it's very easy. You can have essentially chainmail that's completely interlocked within itself, manufactured in metals, which we've done. You can also do it in plastics very easily as well.
Thinking about the organ printing that you mentioned earlier for medical purposes, so today, for example, if we wanted to simulate, you had 3D information about the brain structure, what type of material possibly you could use to print it? So is it only metal, plastic, or could it be more soft type of material? If, for example, a doctor wanted to, let's say, simulate extracting a tumor for a patient, for example, and use that as a...
If you want it to be biocompatible, at the moment people are focusing on things like titanium and cobalt chrome, and PEEK, which is that very specific plastic. There are techniques that are trying to almost deposit cells or more starch-based 3D printing techniques that you can then infuse with the medium you want. So you can actually create a scaffold structure, and then you infuse it with the cells or the structure you want to then create that kind of structure. So it's very R&D at that moment. It's not, no one's really pushing that kind of stuff commercially yet.
Can you give us some idea how long the printing process takes for various sizes of objects?
Sure. You can manufacture, so this part here, this is a spinal implant made in titanium, has the porous internal structure, and it's used if your disc is ruptured and you put it between your vertebrae and you get full fusion into this part. These parts can be manufactured in a number of hours. But what you do is you can actually stack these next to each other in the machine and probably build several hundred at the same time. So that may then increase the time to, let's say, 20 hours, but you've just built, let's say, 500 of those. So if you divide the times, you're actually getting a pretty good rate on the manufacturing of each one.
Because they're so small.
Sorry?
Because they're so small.
Yeah, so time in general, although it's not exact, it's kind of proportional to the height of the object. So something very long and thin is going to take a much longer time to build because the recoat has to keep going back and forth, but it's essentially only melting an area of this big. So what you do with that object is you could just drop it sideways instead, only build this height, and then you can get it a lot cheaper. So there's stacking strategies and how to get these parts best into the 3D printer can dramatically reduce the cost of the parts as well.
Could you give us an idea of the scale of the revenues that you're seeing from different industries and how fast that's growing?
Sorry, the status, sorry?
The scale of the revenues that you're seeing from different industries.
Okay. Medical is becoming very interesting. People in the US are now pushing towards getting FDA approval for 3D printed titanium implants, and I believe you'll get the first one within the next 6 months. This will open up the door for many others just to follow through with that same FDA application, which means medical will suddenly explode. Aerospace has traditionally been very strong. It'll take a very long time probably to be on commercial airlines. For private or defense-type aircraft, it'll be there, and it's moving there much more quickly. Their budgets just to develop tend to be quite reasonable anyway, so even if it's not on the plane, you get funded quite nicely to do the work. Formula One, I think most Formula One teams probably have at least one 3D printed part on their vehicles at the moment, be that metal or plastics. I think probably all of them use it for prototyping for wind tunnel testing. So they'll make their scale model of their Formula One car when they want to try new wing designs, for example. What I'm seeing as a big emerging one is actually tooling. So it's in creating tools for injection molding. And this is very interesting because what you're doing is you're kind of allowing the competition to kind of be even more efficient. By 3D printing a tool, you can design within this tool. And just to give you an idea of what I mean, injection molding is you have a male and female, and you close up these two tools, and you inject the cavity with molten plastic, and you open it up, and you have your plastic part. So nearly everything you see around you that's plastic is probably injection molded. To make this open up and close up more quickly means that the part price goes down. And to do that, you need to get the part to cool down more quickly. So what we can do within the solid tool is create what are known as conformal cooling channels. You can actually create internal snake-type channels where you can pump in cold fluid to cool down the tool more quickly so that you can have a better drop rate. So this is what I see actually, ironically, as being one of the biggest growth industries.
Are there currently any 3D printing techniques for electronics? I mean, at the moment, everything has to be roughly sort of board-shaped. Every electronic device has got this plastic board with what tracks on it, inside it, and that kind of limits the shape. Is it possible to print something that's like a circuit board, but in a more sort of flexible shape or something using these devices?
Yeah. Using the extrusion type of 3D printers, they're already working with multiple materials. And people have actually been able to 3D print batteries, for example, or components that actually can sense their own strain. You can actually have internal sensors by having metal parts within plastic parts, and you can actually change the conductance, and you can have plastic and metal running through within one component. This is a very early stage. It's all at the moment in universities and at research labs. It's not really being commercialized. But multi-material 3D printing is definitely one of the growth areas as well.
I'd like to thank Sia for a very, very fascinating talk. And I'd like to invite everybody to join us in the atrium afterwards for a drink. So, very warm round of applause.